Variable frequency drives are one of the most common energy retrofit recommendations in commercial buildings. Utilities love them. Owners expect big savings. But in the real world, a lot of VFD retrofits don't deliver what was promised. Or worse, they create comfort, controls, and maintenance problems. In this video, we're going to walk through two real-world VFD retrofit examples and show a clear before and after comparison for each one. These are common situations you'll see in existing buildings, and we'll focus on what changes in the system, how the controls work, and where the energy savings really come from. Section 1. What a VFD retrofit is and is not. Most older HVAC systems were designed as constant volume systems. The motor runs at 60 Hz. Air or water flow is controlled mechanically with dampers or valves. A VFD retrofit replaces or bypasses the starter and allows us to vary motor speed based on demand. The energy savings come from reducing speed, not just cycling on and off. At partial load, even small speed reductions can yield large energy savings. But, and this is critical, only if the system can safely operate at those lower speeds. Section 2. When a VFD retrofit makes sense. Good VFD retrofit candidates usually have at least one of the following. Variable demand over time. Long operating hours. Mechanical systems that can tolerate turndown. A control variable we can measure. Let's look at two real-world VFD retrofits and see what changes before and after the drive is installed. The first is a chilled water pump serving a two-way valve system. Remove the existing three-way control valves and associated bypass piping and replace them with two-way modulating valves. This allows chilled water flow to vary with load instead of maintaining constant flow from the supply to the return. Install a variable frequency drive, VFD, to control the pump motor, first confirming that the motor is rated for VFD duty. If the motor is not VFD rated, it must be replaced. Next, install a differential pressure sensor to monitor system pressure as the control valves close. As differential pressure increases, the controller sends a signal to the VFD to reduce pump speed, lowering energy consumption. Finally, verify that the chiller receives the minimum flow required for proper operation. Install a bypass line between the chilled water supply and return near the chiller, sized to maintain minimum evaporator flow when most valves are closed. Next, we have a garage exhaust system. Instead of operating the garage exhaust fan at full speed continuously, install a carbon monoxide, CO, monitoring and control system with multiple CO sensors throughout the garage. These sensors are connected to a variable frequency drive, VFD, which modulates the exhaust fan speed to maintain carbon monoxide concentrations within safe limits. When vehicle activity is low and carbon monoxide levels are minimal, the VFD reduces fan speed, significantly lowering energy consumption. As vehicle traffic increases and CO levels rise due to combustion engine operation, the controller automatically increases fan speed to provide the required ventilation and maintain code-compliant indoor air quality. Poor candidates for a VFD retrofit include systems with constant minimum airflow requirements, fans near surge or stall limits, equipment with no clear control variable. Section 3. The retrofit process. Drawing first. Step 1. Existing system review. Start by understanding what you have. Fan or pump type. Motor horsepower and age. Belt-driven or direct drive. Existing controls and safeties. Step 2. Mechanical checks. You must confirm minimum air or water flow limits, risk of fan surge or pump cavitation, bearing lubrication requirements. Resonance at low speeds for belt systems. This is where many retrofits quietly fail. Step 3. Electrical checks. Electrically, you need to evaluate. Is the motor rated for VFD duty? Lead length between VFD and motor. Grounding and bonding. Harmonics and panel capacity. Older motors can often survive VFDs, but not always, and not without risk. Section 4. Controls, where most retrofits fail. The biggest mistake in VFD retrofits is controls logic. A VFD needs a process variable. If you don't have one, the drive will run, but it won't save energy. Common control variables: static pressure, fans; differential pressure, pumps; flow, less common, more expensive; poor sensor placement leads to hunting, oscillation, and operator overrides; minimum speed and safeties. Every VFD retrofit needs a minimum speed limit; freeze protection; a proof of flow or airflow; fire and smoke overrides. If these aren't clearly defined, commissioning becomes guesswork. Section 5. Why energy savings disappear. Here's what typically happens. The system is commissioned correctly. Occupants complain. Operators override minimum speeds. The fan slowly creeps back towards 60 Hz. 6 months later, the VFD is running, but savings are gone. Energy retrofits only work if the control strategy survives turnover. Section 6. Estimating and scope pitfalls. From an estimating standpoint, VFD retrofits fail when scope is incomplete. Commonly missed: sensors and tubing, controls programming and graphics, electrical rework, commissioning and trending, owner training. Most change orders on VFD retrofits are not mechanical, they're controls. Section 7. Commissioning and turnover. A successful VFD retrofit includes trend logs at multiple load conditions, set point documentation, operator training, written sequences of operation. If you don't lock this in at turnover, the system will revert. VFD retrofits can absolutely deliver energy savings, but only when the mechanical system can handle turndown, the electrical system is evaluated properly, the control strategy is designed, not improvised. If you found this video helpful, be sure to check out our HVAC and plumbing estimating spreadsheets to streamline your construction bidding process. Check out our HVAC, electrical, and plumbing construction forms to help you run your business, and explore our online courses for in-depth training.